Well, hi there, boys and girls. Hope everybody had a great weekend. We're getting ready to start our derivatives unit, and we're going to start off derivatives by reviewing a simple slope formula. And we are not going to say the word slope, but we're going to say the word average rate of change. And we're going to be using something called a secant line. And the secant line is simply a line that connects 2 points on a graph. And we're going to take those 2 points and we're going to find the slope between those 2 points. This formula is not scary at all. So let's just take an example here. Let's say that I have this point here, A, on the x-axis, and I'll come up here to this little dot here, and we're going to call that f of A. Whatever that y value is, that's the function value at A. So here's a y coordinate, and this is an x coordinate. And let's go further on the x-axis here. Let's come out here to, I'll just say a second point, and I'll call it B. And I'll go up there and I'll label that y coordinate. What do you think I'm going to label that y coordinate? Well, that's going to be f of b. So again, you've got a y coordinate, and we label that f of b. So that's like f of x is your y coordinate. Now, if I were to take and just connect these two dots just anyway, it doesn't really matter. Let's just say that was my graph. When we connect these 2 points in a straight line, this is going to be called a secant line. So let me just show you this right here. All right, the slope of that line in black is going to be called we're going to call that the average rate of change of our function. So we're just connecting the endpoints, and we're going to find the slope of that line, and that's like the average slope of this graph. This graph went up, sort of flattened out a little bit, came down a little bit, and then went up again. If we find the slope of this black line, it's the average slope of all of those x coordinates between A and B. So let's see if we can't calculate that slope. So I've got a point A, comma, f of A. That's right here. And I have another point over here, B, comma, f of B. Now, how do we find slope between 2 points? Well, you know your formula is y2 minus y1 over x2 minus x1. That's on your tax chart. The form that we're going to be using, though, we're going to have a little different notation. I'm going to go back to blue here. Our notation is going to be f of b minus f of a over b minus a. And this is the formula for the average rate of change. Notice it's just y2, f of b was y2, minus y1, f of a was y1, over x2 minus x1. This is just a slope formula, but we're going to use this function notation, and we're going to call that the average rate of change. And that is the slope of this secant line. And this line in black, I'm calling that the secant line because it connects those 2 points. Let's go take a look at a physical example here. I want to get to my other graph. Okay. So let's just do a real easy one out of a table. An average rate of change over 2 to 4. So here I've just got a little box. It's got some times, 2, 3, 4, 5, 6, and f of those times. So like these are positions, 1.8, 3.4, blah, blah, blah. Now the average rate of change on this interval from 2 to 4, we look at the time 2 to 4, so we're going to just narrow our eyes right in here. So our average rate of change is going to be f of 4, that's the right-hand endpoint, minus f of 2, that's the left-hand endpoint, over 4 minus 2. So let's actually do that calculation. F of 4 is the y value at 4, and that y value is 4.6. F of 2 is the y value at 2, and that is 1.8. And then, of course, we have 4 minus 2 down here. So I've got y2 minus y1 over x2 minus x1. So what do we get here? This is 2.8 over 2. And when we divide those, we get 1.4. Now, what does that tell you? That just tells you the average slope was almost 1.5. So this graph was between 2 and 4 was increasing, or it was going up because we got a positive slope. That's what that tells us. Take a look at another example. Now we're going to actually have a physical example here where I've got it in terms of motion. So if we've got these 1, 2, 3, 4, 5 time frames, or these 5 data points, and we've got position at those 5 points. And we want to find the average velocity in units per second over 10 to 30. And the way we find average velocity from a position graph is we just do our average rate of change formula. And I'm going to show you why it works out to be velocity. So whenever you connect 2 dots and you make a secant line on a position graph, the slope of that line is your average velocity. So let's see here. We want to go from 10 to 30. So we want to do, I'm going to call it F, even though this doesn't say F notation here. F of 30 minus F of 10, because we're going from 10 to 30, all over 30 minus 10. So that would be 44 minus 12. There's F of 30 minus F of 10, all over 30 minus 10. So what is that? That is 32 over 20, which is 1.6. 16 over 10. Now let's take a look at these units. What was the 44 and the 12? Physically, what did they represent? Well, it's like a position. You could have called it feet, or maybe miles, or it was a position statement. So 44 may be feet minus 12 feet. So what would we have up here for this 32? The units would be, like feet. Now on the bottom, what were those units? Well, this was 30 and 10. Those were seconds. And so you would end up with something like feet over seconds. And that's a velocity unit, feet per second. So when you do an average rate of change to a position graph, you're going to get a velocity, an average velocity. So this one here, we don't know it was feet. So I've just got to say units per second. So when you connect and you do a secant line graph on a position graph, the slope of that secant line represents an average velocity. So what does this mean? We were going forward. We were moving forward because we got a positive velocity at an average rate of 1.6 units per second. Now, were there other times in here where we were going faster than that? Well, yeah, sure. I mean, look at this from 20 to 30. We increased by 18, which is a bigger increase from the 10 to 20. From 10 to 20, we'll increase by 14. So, yeah, maybe we accelerated in there, and maybe the velocity was different, but the average velocity from 10 to 30 is 1.6 units per second. We will take a look very soon this week at something called instantaneous velocity, and we need the derivative for that. But right now we're just doing average. Let's take a look at one last example. So I've got this position of an object given by this quadratic t squared minus 4t plus 7, and we want the average velocity over the interval from t to t plus delta t. This delta t means change in t, so it's basically some time unit after the t. So the delta t, you're going to treat it like its own variable. So let's take a look at that. We want to do s of, because my function is labeled by s of t plus delta t minus s of t all over t plus delta t minus t. So it's like y2 minus y1 over x2 minus x1. So let's keep going with that. Let's do that. Now, s of t plus delta t means plug t plus delta t into this equation. So I've got to do the following. I'm going to have to drop down to a not so thick pencil. Let's go back to purple. All right, so s of t plus delta t would look like this. So there's the t squared, but we're actually plugging in t plus delta t for t, so that's that squared, minus 4 times t plus delta t plus 7. There is s of t plus delta t. And then we're going to do minus, and you better do parentheses here because it's really easy to not distribute that and make a mistake, minus s of t. Well, here is s of t. T squared minus 4t plus 7. And that's all over t plus delta t minus t. Those t's are going to cancel, and I'll just have delta t down here. Now, we're not done. We actually have to figure out this mess up here in the numerator. So I'm going to distribute t plus delta t squared, where you have to FOIL it out. We all know it's not just this squared plus that squared. So it's t squared plus 2t delta t plus delta t squared. That's squaring that all out. Now let's distribute the 4. Minus 4t minus 4 delta t. And then we've got the plus 7. And let's distribute our negative. Minus t squared plus 4t minus 7. All over delta t. I don't even know if I'm going to have room for all this. It's a weird delta there, Mr. G. All right. So let's see if this cleans up at all. Let's see, I've got a t squared here, and later on I've got a minus t squared. Well, that's sort of cool. Those cancel. What else happens? I've got a minus 4t and a plus 4t. I've got a plus 7 and a minus 7. So let's see what we have left. We have 2t delta t plus delta t squared minus 4 delta t, and that's all over delta t. So it looks like we've got something that we can cancel here. Let's factor a delta t out of the top. So that would be 2t plus delta t minus 4 over delta t. Those cancel, and we have our answer. This is the average rate of change for that function over the interval t to t plus delta t. Now we're going to take a look at what something, well, it's called the derivative. This is the average rate of change, and later on this week we're going to let delta t go to 0, and you're going to see what I mean by that, and that's going to be our instantaneous velocity. But right now this is the average. Okay, so I will see you guys tomorrow.